right, dual credit stat students, we are continuing with learning about hypothesis testing, and today we're going to be writing some notes down as opposed to the worksheet that you guys had yesterday. So make sure you got your notebooks out, and you can also have out that worksheet that we did yesterday. Instead of writing anything, because all I have is this mouse, and so like I could sit here and try to like write out things, but that's just not as efficient. I'm probably be better off just to actually type things, and you guys can write them in your notes. So in your notes, we can start our new section finally. So this is Unit 8, Chapter 9. This is hypothesis testing. Okay, so you can just sort of title a page, start a new page in your notebook, and that's what you can start with. Okay, so the first thing that we want to do is we want to define what a significance test is. So this will be a definition here for this. So a significance test is a formal procedure for comparing observed data with a claim. We'll put in parentheses hypothesis, because it's called hypothesis testing, whose truth we want to assess. If we think about this definition, and also if this video needs to be paused, go for it. But if we think about this definition, yesterday we have a claim. Miss Gallus claimed she's an 80% free throw shooter. And if we're thinking about our definition, we want to run a procedure with what we observe, the 50 free throws, to compare to that claim. We want to take that data and assess the truth of that claim, the hypothesis. Okay, and I like how this worksheet kind of broke it down, that there's two options. She is an 80% free throw shooter and just had bad luck, or she's not an 80% free throw shooter. That's a very practical way of talking about it. Now, the formal part of this, when it says we want a formal procedure, obviously we don't want to just sit and like guess, okay, is it good enough? Yesterday we had broke it down to a percentage, which we're going to talk about that percentage a little bit today. And we got a reasoning behind it. We got through some of the logic of it to make a claim, or to decide whether that claim was valid, and we decided that it was not, because if she was an 80% free throw shooter, but then her original data, she shot 64%, that just never happened in our simulations. So it doesn't really make sense that that would be true. Okay. So we're going to go ahead and you can sort of make a section. What do I always do? I always do like little stars in here. So we're going to talk about the language of significance tests. Okay. The first thing that we do is we state hypotheses. Okay. And you have two types of hypotheses. Okay. And let's actually add, it's not just the language, but the language and logic. Let's add that, the language and logic of significance tests. What are we trying to do here? So we want to state the hypotheses. You have two types of hypotheses. One is called the null hypothesis. I'll write out a definition for that in a second, and then we'll also have a new symbol that goes with this. Leave yourself some space. I'll go ahead and make that indentation here on our notes here. You also have the alternate hypothesis. So those are the two options. I will be adding a symbol at the end of these definitions after I do that. So we have a new symbol. It's not anything crazy, but let's go ahead and write down these definitions. So the null hypothesis is the claim we seek evidence against. I'll put a little semicolon there. It is the statement of, put in quotes, no difference. Example. And I'm going to copy what we did yesterday. Right here. Miss Gallus claims she is a 80% free throw shooter. So we have that as our example. Miss Gallus claims she is an 80% free throw shooter. And then lastly, the symbol for this, and I'm just going to insert a little math equation here. So this has a subscript, but it's H subscript 0, okay? H sub 0. That's what we're going to see as the null hypothesis, okay? This blue. Okay, so the alternate hypothesis is the claim about population we are trying to find evidence for. Okay. Example. We could take this. We'll just take Miss Gallus again. So Miss Gallus is exaggerating. Okay, there it is. So that would be an example of an alternate hypothesis. Now the symbol for this, there's actually two potential symbols, okay, that you could use. In this class, most commonly, you are going to see H subscript A, okay? Now that could also be shown as H1, okay? A for alternate, right? Or they have the 0 here, so 0 means not or null, and 1 is yes. And you think about this as binary. It's one of these two things is going to be true. And that should be sort of making us think about these right here. These are the null and alternate hypothesis. If you would like to right now, go back to this sheet and you can actually write that on here. This is the null hypothesis. Okay. She is an 80% free throw shooter, just had bad luck. So we are still kind of with her on that, or we're finding evidence that the alternate would be true, that she is not an 80% free throw shooter. So HO is true up here. HA is true for the second option. So it's not exactly the hypothesis. We're going to show you how to set that up, and you'll have a lot of practice in the MyOpenMath with this. But that's at least getting us thinking a little bit about those, and we'll practice setting up the back page of this. I said I promised that we'd come back here and start talking about these, but I want to talk about some of the other stuff as well. Okay, I want to get through. I want to go through all the logic and the language just through this first example, and then we'll do the second one as our example, and we'll use the Inspire to help us out to get some numbers. Okay. We're actually going to go ahead and write up our null and alternate hypothesis in a proper format. So let's make a section here, writing hypotheses. So this is kind of a new section. If you want, we can just put like a bunch of lines here. Partition this. So writing hypotheses. We will do this example with Miss Gallus still. So Miss Gallus free throws. I'm actually going to bump this to the next page. Okay, so her free throws. And so we want to create these hypotheses. So we'll go ahead and you always write your hypotheses with the null hypothesis first, page 0. I'm going to move that over, okay, with a little colon, and then we're going to copy that, and we'll put the alternate right here. So we have that. Now, you always want this to be in terms of the parameter being estimated. So let's actually write that a little bit above. So we'll say this: hypotheses should always be written in terms of the parameter. We identified our parameter. That was where this began. All of Miss G's free throws. It's her ability to shoot a free throw. Okay. So what we're going to put here, we know that the parameter of interest is a population proportion. So we're going to put P. Okay. And that goes for actually both of these. So let's put P for both of these. So we are saying the null claim, the one that we are seeking evidence against, it's the statement that's no different. It's really just the claim that she made. It's what's pre-existing. P is equal to 0.8, 80%. That's what she said. She is an 80% free throw shooter. Okay. What we're trying to show is that she was exaggerating. Okay. And what we wanted to show with that was that we think that since she's exaggerating, we think that it's less than. Okay. Not just that she's not an 80% shooter, she's actually worse than 80%. And so with that, we're going to use a less than, and we'll put the 0.8 in there. Okay. And there it is. That is a correct, that would get you credit on the My Open Math, just setting up a hypothesis. And that's how you do it. We do want to add one more little part to this, which is we want to define what P actually is. Okay. So P is equal to, P equals the true shooting, we'll say, no, true free throw shooting ability for Miss Gallus. So that's what this proportion is. So she said it was 0.8, and we think she's exaggerating. Okay. All right, cool. So we're going to write down a few more rules. So put a little star, more about hypothesis. Or we'll say hypotheses. Okay. Okay. Couple of bullet points. So we'll make a list of bullet points. Hypotheses. This is kind of repeating what we've already written. Always refer to a population, not a sample. Okay. Be sure to state, I'm not going to, I'll just write it like that, HO and HA. In terms of the parameters. So before I write on here, so what we're going to use, we're going to be using either mu or we'll be using P. That's it. That's all that you should ever see for your parameter. Okay. That's all that you should ever use in a hypothesis. So if I were to look at this, and I'll go ahead and tell you that there will be some questions. We'll look at one in a second. But if I were to tell you that that this was in fact not just P, but if we wrote it as P hat, this would be a problem. We never write it like this. Okay, let me actually pull up a problem so we can see what I'm talking about. Here's one right here. Okay, here's one right here. So it says, to determine if having children within the first 2 years of marriage increases the divorce rate, where P is equal to the proportion of marriages that end in divorce, we should test the hypotheses. As we look at these examples, and I'm going to snip this so that I can write on it. So let's look at this. Okay. All right. So right off the bat, I would get rid of B and I would get rid of A because I can't have these. That doesn't work. We can't have this expressed in terms of P hat. Now, I'm sure you said, I think, where are they getting the 0.5 from? Well, it says the proportion of marriages that end in divorce. So I think a lot of us know that 50% of marriages end in divorce. So that's where they're getting the 0.5 from. So C, D, and E so far look fine. But what I just did there was show this rule that we're talking about. So we use mu or P, never use, let's insert those, never use a P hat. Start with X bar though. So we never use X bar or P hat. Or there it is. Okay. So we never use these symbols in a hypothesis setup when we're setting that up. Okay. Okay. So let's move to the next thing. It is never correct. Write the hypothesis about a statistic. That's what this is about. So really I could have put this down here. Whatever, it's already there, about a statistic. So there we go, we have that. Next. HO is always equal to, actually add some more symbols in here. It's always equal to, greater than or equal to, or less than or equal to, or greater than or equal to. That's it. And for this, we typically use equals. Okay. I would say 95% of the time we're using this equal sign to do this. Okay. So this is going to be more commonly seen. So this that little tidbit of information actually gives us help on this problem here. So right away, I can actually scratch out one of these. So it's C that we can get rid of because it has this symbol right here. Okay, so the null hypothesis is always going to be an equal sign. Now in your MyOpenMath, it will sometimes be like a greater than or equal to or a less than or equal to, which is fine. So you'll just have to work through that. Okay. So yeah, okay. Now we want to figure out what to do with the last part of this, and so we'll write about that. Excuse me. So the alternate hypothesis is always, I better capitalize that, always, and you've got three options for this. It'll be a not equal to, a greater than, or less than. Okay, based on what the problem states. Okay, so we're going to look at this problem here, and you'll notice here, to determine if having children within the first 2 years of marriage increases the divorce rate. So it's established that 50% of marriages end in divorce. So we're wondering if having children within the first 2 years increases that. And so the one that shows that would be answer choice E here, because it is showing that the proportion gets larger. Okay, so not this one here. All right. I want to show one more of these. So here we have a biology question. It says the average growth of a certain variety of pine tree is 10.1 inches in 3 years. A biologist claims that a new variety will have a greater 3-year growth. A random sample of 25 of the new variety has an average 3-year growth of 10.8 inches and a standard deviation of 2.1. We want the appropriate null and alternate hypothesis. Okay. So first glance, first thing you should be looking for with this is, are these symbols in order? So is the null hypothesis one of those 3 symbols? If it were any of these, that would be a problem. So as we look on this, this is good. All of these have equal signs. Okay. And then over here, we want to make sure that none of these are equal signs. So it looks like all the symbols are good. We also notice that it's mu because we see the word, we see average, we see the word standard deviation here. So all that we've done with confidence intervals and sampling distributions, we know how to differentiate between whether it's mu or p. Okay. So what we need to determine is what goes where. They are trying to, it says right here, a biologist claims that a new variety will have a greater 3-year growth. So we know that it shouldn't be B because that's not equal to. How that would show up is if it were different. We'll write about that in a second. Okay. And this one is less than, and this one is also not equal to. So we know that it can't be these because of this idea of we want to show that it's greater than, and that's why the symbol for A or C would be better. Now you'll notice we have to decide, is it 10.8 or is it 10.1? Those show up. I'm actually going to highlight these. So this here and this here, these show up here. So we have 10.8 right here and 10.1 right here. We said that in one of our rules, the hypothesis should always refer to a population, not a sample. So we're going to sort of lean into that rule to help us here. Which one of these numbers is talking about the population and which one is talking about a sample? Well, if you read the second number on here, we'll notice that this number is talking about the random sample that they took. Okay. And the way that this one here reads is that it's talking about the entire population. Okay. And so with that in mind, that's why we would not choose A on this one. We would in fact choose C as the correct answer because it's in terms of the population. So they tell us that it's 10.1. That's what's known. And then we're trying to find evidence that the new variety is going to have a greater growth than that. Okay, so C is the best choice on that one. I'll probably have this problem set. I'll have this get printed for you guys so you have something to practice with. Some of this you can't do though, because a lot of it, several questions in here are AP, but that's okay. We will probably be pulling some more examples from this. As far as my open math goes, the first 10 questions are all setting up hypotheses on here. So it's all setting up just all these different hypotheses. We do want to go ahead and talk about this idea right here. Okay, the idea of tails. So we're going to go ahead and talk about that and write about that. Right. Okay, so let's talk about one tail or one-sided tests. Okay. So these are the tests. We don't need bullet points for this. I want the star actually. So whenever we're saying that the parameter is greater than a value, and these are all in terms of the alternate, by the way. Actually put that in front. Oops. Okay, so if the alternate is that the parameter is greater than a value, or the parameter is less than a value. So anytime you see the word greater than, or less than. That's how you know it's one-sided. It's one, we call that one tail, single tail. Okay. And then we have, go ahead and talk about the two-tailed tests. Two-tailed, we'll also call this, sorry, two-sided tests. This is when the alternate hypothesis is, and we'll insert equation here. This is when it is not equal to a particular value. What this means, what you would see for this is different or changed. It's either different or it's changed. Like if they expect that this parameter has changed. Okay, that's what you'll be looking for. I think we saw that in that last question. This one was increase. This was increase. As you read problems, you're just looking for that language. So for instance, let's just look at this one. This is question 3. On this one, you got the null is that it's equal to 70, and then the alternate, here's that H1, is greater than 70. So this would be a particularly, we need to specify direction as well. So you have the direction left or right. So let's go back and add that to our notes. What I always say as a trick is you look at the way that inequality is pointing. So it's pointing that way. Greater than means going to the right. If we think about like the x-axis, this would be right-tailed. Okay, that's right-tailed. Okay, and in front of this one, this would be left-tailed, where the parameter is less than. So less than is left, greater than is right. So that's how I'm glad that I looked at that problem so that I could specify that. So this one is in fact a right-tailed test on this one. I don't know if y'all have the same question or not, but that's what that's talking about. And now you can use that. So if we see two-sided tests, it's two-tailed, one-sided. Like now you know what that language is. So here we have another one there. Gives you all these different instructions on typing in different hypotheses. Okay. All right, so let's continue with our test. We'll go back to that example with the free throw shooting. Let's go ahead and write some more. All right, so we have for our example, I'm going to copy this down. Example continued. Dallas free throws, we have this here. Okay. All right, and so what we're going to do is we want to let's also define what kind of test this is. This is a left tail test is what we would call this. All right, and we have already gotten we know the statistic that we used for this. We got our p hat value. So we have p hat equals, and we saw that she made 32 out of the 50 shots, which ended up being 0.64. Okay, so that's what we saw. Now, what we did in the other notes was we used StatKey to help simulate this. Okay, and we built a sampling distribution. So I'm going to pull that up again for us, and we're going to do this again, but this time I'm going to make a very very large sampling distribution. So we're going to put this at samples of size 50 again, and we're going to have the proportion set at 0.8. Okay, at 0.8, and I'm going to generate 1,000 samples. Okay, so here is our, I'm going to zoom. Actually, I'm going to snip this. Okay. So we have this, and we have a sampling distribution of what we would expect to happen. Okay, this is what we would expect to happen. You'll notice that computer's acting crazy. It doesn't really look like it's a normal distribution. It doesn't look perfect, but we know how we can check to see if it is normal. I am going to take this and I'm going to paste it into my notes. You guys don't have to do that yet. Okay, you don't have to do that yet. I'm going to move this down. Okay, but in your notes, what we can put, okay, is we're wondering, would, if I took many samples of size 50, if this was of a random sample from this, what would the sampling distribution end up looking like? So we'll insert a text box here. I should have paused the recording instead of make y'all watch this. So here's what we're going to write. Would sampling distribution be normal? Okay, that's what we're going to ask. Right now, this doesn't really look normal. It looks like it's kind of skewed to the left, but we know how we can check this. Okay, we know how we can check to see if it would be normal. And that would be using the large counts to see if it is. So it's n times p greater than or equal to 10. Let me actually put this in an equation. Times p is greater than or equal to 10. And then we have, get my formatting correct here. Then we have n times p is, sorry, no, n times 1 minus p is greater than or equal to 10 as well. Now you'll notice we don't actually have we don't know what the true population parameter is. We don't know what p is for this. So we're actually going to end up using p sub 0 for this in these places. So you can add that to yours. Okay. And so let's see what this will end up being. So n is, we have 50, p is 0.8, or p sub 0 is 0.8. And then on the other end, it would be 0.5, sorry, again, and 0.8 again. Okay. And I think for both of these, so 50 times 0.8 is 40. So we do know that 40 would be greater than or equal to 10. Messing this formatting up so bad. And then we know that the other one, one moment. So that would be 50 times 0.2. So that's 10 exactly. So both of these conditions are in good shape. So these are true. Okay, so we know that this is a normal distribution centered around 0.8. And so what we're looking at is what's the likelihood that we would get this, okay? So we'll come back to this. What we have to calculate is something called a p-value. So this is quite important. So a p-value. A p-value is, scroll up here. Let me make this font bigger as well. P-value is a value. Sorry, no. A probability. Assuming that the null is true. Add some commas. So it's a probability assuming the null is true that the statistic would take on a value as extreme or more extreme than the one actually observed. Okay. So what we did yesterday was we kind of made a p-value out of this. So here's for our definition, it says it's a probability that the statistic, guess what the statistic is? The statistic is this, 0.64. Okay. What's the likelihood that we would have this happen, assuming the null is true? So what's the odds this would happen or something more extreme? And so back on StatKey, that kind of is something that we can do. I don't know what happened to my distribution here, but let me do that one more time. So samples of 0.8. I will do 1,000 samples here. I need to actually split my screen so you guys can see this. So what's the odds that I would get something? So here's 0.64 right here. So we do a left tail. What's the odds that I would get 0.64 or something more extreme? Right here we get 0.0050. Yesterday in our notes, we got that's not y'all. This one. We got 0% because out of our 102 of these, we didn't have it happen once. So we had a p-value of 0. So we did make a p-value yesterday. We just didn't call it that. But this is very important. These p-values. So basically, it's going to boil down to most questions. In particular, I'll show what a lot of these are going to look like going past question. Talk about types of error in a second, or we'll talk about that later. There yet. Right here. So this is where, like in a lot of questions, you're going to have to calculate the p-value, and then you'll make a conclusion based on that. So if we were working a question like this, we would have to get a p-value to help make a conclusion, and then we'll talk about also making conclusions in a moment. Let's talk about some more facts about the p-values. Okay, some more bullet points. Small p-values are evidence against the null hypothesis because it shows that the result in the statistic is unlikely to have happened randomly. if we think about this, that was what the sheet had said on here, right? So the null is, okay, she's an 8% free throw shooter, but she just had bad luck. And then option 2 was, no, she's not. So we're saying, okay, could this have just been bad luck? 0.64, that's what we're trying to assess here. That's the logic of the significance test is, could this have just happened randomly? And we're saying no, because that value is so low. And in particular, on our simulation, we're saying, okay, that only happened 0.05. That's not, yeah, it's 0.5% of the time. That's a tiny amount of probability. So this is just probably, she's probably not have bad luck. Okay, she probably doesn't have bad luck. So then we'll talk about this. So large p-values fail to give convincing evidence against the null hypothesis. Okay. We do have, this is a very important statement that we're about to write here. This is the most important piece, and we'll have a sort of a mnemonic device for it. So if the p-value is lower than, we're introducing an idea called alpha. You've seen alpha in that z sub alpha over 2 context for the critical value. I'm going to go ahead and insert the symbol in here. Let me find it. It's the Greek it's the fish. There it is. So if the p-value is lower than alpha, then the results are statistically significant. This is very important to remember, because this idea of alpha, which, by the way, problems will be giving you alpha. They'll tell you what that is. But here is the saying that you can use to help remember this. If the p-value is low, reject the hoe. I remember this is something that my stats teacher in college taught me, and I can never forget it. And that's what this is saying, is essentially what this third bullet point is saying. Because what's going to happen at the end of a significance test is your conclusion is going to be to reject it or fail to reject it. We're going to write that down in a second, but I also want to define statistically significant. So we can write that down below. So statistically significant, if our sample result is too unlikely to have happened by random chance, we reject, show, and say there is convincing evidence for HA. Okay. Let's put a star conclusions. Okay. You have 2 options. This is it. These are the only 2. 1, you can reject the null hypothesis or fail to reject. That is it. That's all that can occur. Those are the 2 choices. And it's all based on this statement right here. If the p-value is low, you reject the hoe. So if the p-value is not low, you fail to reject the hoe. Okay. So that's really what it breaks down to. That's really what it breaks down to. And I'm going to add that over here. So if p-value actually put it in an equation here. So p-value is less than alpha. You reject. And if the p-value is greater than alpha, you will fail to reject. So that's pretty much what it boils down to with the logic of testing. We wrote this. I wasn't really ready to get into that yet. I probably should have waited. We'll come back and talk about this in a second. I don't think we needed it to understand the logic, but I think the real thing is this: we start with our hypothesis, we build sort of this model around this what we're assuming to be true, innocent until we prove it guilty, kind of. Then we take a sample here and we compare that to what should occur, which this is what we would expect if this were true, if that p hat is true. And then we notice that no, it's just unlikely. So for our example here, our p-value was like 0.005, but we'll actually calculate that more properly in tomorrow's lesson. This video is already at 46 minutes, so I'll stop there and you guys can work on my open math for the remainder of the time.